Okay, so good afternoon, everyone. Let's talk about propositions. Propositions has only two conditions. The first one, it is a declarative sentence, and the second one, it has only one truth value. By truth value, we mean the truthfulness of the proposition. So we have only two options in here, whether it is true or it is false. Now, for a sentence to be considered as a proposition, it should contain these two conditions. The first condition should be satisfied, and the second condition should be satisfied also. If the first condition is satisfied, but the second condition is not satisfied, then it is not called a proposition. The two conditions should be satisfied. Alright, but before we continue on the propositions, I'd like to introduce to you the way of representing sentences. So we have two options. It could be in mathematical form and it could be in English form. For example, the mathematical form of a sentence x plus 1 is equal to 2. Well, this is in mathematical form, but we can also write this one in English form. This becomes x plus 1 is equal to 2. Alright, now aside from the mathematical form and the English form, we can also represent the English form into an argument form, or we can use propositional variables like P. So we will suppose that the statement P is our sentence x plus 1 is equal to 2. Now again, a mathematical form can be represented by using an English form, and an English form of a sentence can also be represented by a propositional variable. Now let's continue our topic. Let's try to identify if the following sentences are considered as a proposition. Okay, let's have, for example, the sentence. Let's have the example. Let me write it here. 2 plus 1 is equal to 3. 2 plus 1 is equal to 3. Let's have the other sentence. Emma is a pretty girl. Let's add another sentence. Let's say, are you hungry? And the other sentence, I hate you. Okay, so let's start identifying whether each of these sentences can be considered as a proposition. Now again, we only have two conditions for that. Okay, let's begin with the first sentence. 2 plus 1 is equal to 3. Is it a declarative sentence? Now, what is a declarative sentence, by the way? We have different types of sentences: the imperative, the interrogative, the declarative, and the exclamatory sentence. So in this case, the first sentence is a declarative sentence. It states a fact. It gives us information about something. Now take note, if we will convert this mathematical form into an English sentence, we will have 2 plus 1 is equal to 3. So it is a sentence, a declarative sentence specifically. It has a subject and a predicate. Now it satisfies our first condition. What about the second condition? Does it have only one truth value? 2 plus 1 is equal to 3. So let's try to solve that. 2 plus 1 is equal to 3. On the left side, we'll have to add this. 2 plus 1, that is 3. The same goes for the other side. So this means that statement A is a proposition and its truth value is true. Now let's have sentence B. Emma is a pretty girl. So let's see if it satisfies the first condition. Yes, it is a declarative sentence. But what about the second condition? Does it have only one truth value? So if you were to ask someone whether she finds or he finds Emma as pretty, the other will probably say, yes, she is pretty. But the other individuals will disagree that no, Emma is not pretty. So there are two truth values. The true for the others, it's true that Emma is pretty, and false for the others, they do not agree that Emma is pretty. And since this instance violates the second condition, therefore it is not a proposition. Okay? It's not a proposition. Take note, this is subjective. What do we say by subjective? What do we mean by that? It's simply based on the emotions or the opinions of other people. So it could be true to other, and it could be false for the rest. There are two truth values. It does not satisfy the second condition. Now let's have statement C. Are you hungry? So let's consider this one. Are you hungry? It has a question mark. And if it has a question mark, it is asking a question. If it is asking a question, then it is an interrogative sentence. If it is an interrogative sentence, then it's not a declarative sentence. If it's not a declarative sentence, then it does not satisfy the first condition. So this is not a proposition. Again, any of the conditions that will not be satisfied, automatically your example or sentence will not be considered as a proposition. Now let's have statement D. I hate you. Okay, let's see. This is a sentence, but it is not a declarative sentence. It is an imperative sentence. Okay? No, exclamatory sentence rather. This is an exclamatory sentence. Okay, so this is not a proposition. Now what if I have here, let's have another example. Let me write it here. Statement D. Oops. Let's have another example. Statement E. Right? E. X plus 1 is equal to 3. And let's say we have another sentence here. Statement F. Let's say 2 plus 3 is just equal to 5 plus 3. Okay, so let's try to identify this sentence E first. X plus 1 is equal to 3. Okay, x plus 1 is equal to 3. This is a declarative sentence, so it satisfies the first condition. But for the second condition, remember it has only one truth value. It means there should be one truth value. But in this case, we cannot determine if the statement is true or false unless or not unless we have a specific value for x. So in this case, it's not a proposition because the truthfulness of this sentence depends on your value of x. So this will only be true if, let's say, for example, x plus 3, let's say x plus 3 is equal to 3. such that x is equal to x plus 1 rather, okay. X plus 1 is equal to 3 such that x is equal to 2. So substituting 2 to x, will have 2 plus 1 equals 3. 3 is equal to 3. So this can be a proposition and its truth value is true. Or we can have like this. X plus 1 is equal to 3 such that x is equal to 4. Now we'll be substituting 4 to x. 4 plus 1 is equal to 3. 4 plus 1, that is 5, equals 3. We know for a fact that 5 is greater than 3, so this is false. However, it can be considered as a proposition. So it's a proposition and its truth value is false. Now let's have the next statement, statement F, or sentence F. 2 plus 3 is equal to 5 plus 3. Now let's combine this. 2 plus 3, that is 5. Copy the equal sign, and 5 plus 3, that is 8. This is a proposition. It satisfies the first condition, but it is false since 5 is not equal to 8. So again, the main thought in here is just to satisfy the two condition for your sentence to be considered as a proposition. Now, in English, we have also connectives that we usually use to combine two or more sentences. It's the same with logic. However, in here, we will be using, or we will be using logical connectives. They're called logical connectives. Okay, so let me write it in here. Logical connectives. Now let's begin with the first connective, that is the negation. Okay, the negation is given by the symbol, this one, and it's read as not. So if I have here a propositional variable p that represents my statement or my proposition, then the negation of p will be not p. So let's suppose that my statement P or my proposition P will be 2 plus 2 is equal to 4. Then if I will take out the negation of this particular proposition or the not P, it will be 2 plus 2 is not equal to 4. So you'll only be writing the opposite or the other way around, right? So you'll be contradicting your statement P. Okay, now how do we find or how do we look for the truth values of the negation? Let's consider the truth table in here. We only have one variable in here. So the given formula for that, how many rows will we be making for these? That is simply given by the formula 2 raised to n. 2 is the base, that's constant, and n here is your variable. So let's copy 2, and in this particular example, we have one variable only. So that's 2 raised to 1, or simply 2. That means we will be making 2 rows. So for the 2 rows, you will divide that into halves, or we divide this into 2, then we'll have 1. It means we start with 1 true followed by 1 false. This will be your pattern. So true and false. Now take note again, we have mentioned negation is just the opposite, or the not P or the negation of P is just the opposite of your statement P. So if I have here true for P, then my not P would be false. If my P will be false, then my not P will be true. Now let's go on to the second logical connective that is called conjunction. Alright, let's write it here, conjunction. The conjunction is given by this symbol. It's like an inverted V and it's written or it's read as and in English. Suppose that P and Q are statements. Okay, if they are statements, once I use conjunction to connect these two statements, then I will have P and Q. Or you can read this as the conjunction of P and Q. Suppose that my statement P will be, it is not raining. Okay, it is not raining. And my statement Q will be, or my propositional variable Q will be my proposition, it is cold. It is cold. You might confuse yourself with propositions and statements. So they're just the same, but in mathematics, we usually call that as a proposition. Okay, now if I have here the statement P, it is not raining, and statement Q, it is cold, then my P and Q will be like this. So our P, it's the statement, it is not raining. Let's just substitute. It is not raining. We have this symbol, conjunction, in English that is and. So we'll write down and in here, followed by our Q, which represent the statement, it is cold. So your P and Q will be, it is not raining and it is cold. Now, how do we deal with the truth values of these compound sentences involving conjunction? Okay, so for the conjunction, it will only be true, or this proposition P and Q can only be true if both P and Q are true. Okay, so let's make a truth table. We have P, we have Q. This is for the second variable, and we have the compound statement P and Q. Now we'll have to see its truth values. How many rows will we be making? Again, use the formula 2 raised to n, that's equal to 2 squared. 2 squared because we have two variables in here, P and Q. So this gives us 4. It means we will be making 4 rows. One, right, for a while. 1, 2, 3, and 4. Okay, now this 4, we will divide this into 2 and we'll have 2. So this means the pattern will be 2 true, 2 false. That is for the first column, right? 2 true and 2 false. Now, on the second column for Q, we have 2 in here. 4 divided by 2, that is 2. Now, the 2, we will be dividing that again by 2. So, 2 divided by 2, that is 1. Right? 2 divided by 2, that is 1. So, the pattern will be 1 true, 1 false, 1 true, 1 false, and so on. So, this is true, this is false, this is true, this is false. Now let's go and get P and Q. Again, P and Q will only be true if both your P, your Q are also true. So we have true and true, that is true. True and false, that is false. False and true, that is still false. And we have false and false, that's still false. So you see, it will only be true if both of the propositions are true. Alright, now let's continue to the next connective. Let's have here the third logical connective is the disjunction. Disjunction is given by the symbol. It looks like a V, but it is a disjunction, and it's read as or in English. So suppose my P and Q are statements. If I will be using disjunction to combine these two statements, then my compound statement will look like this: P or Q. Alright, now let's say that my statement P will be it is raining. My statement Q will be it is cold. So my P or Q, or the disjunction of P or Q, will be like this. Substitute the statement P, that is, it is raining. So we'll be writing that down. It is raining. Alright, not a period, not yet. And then we have here disjunction, or in English, that's the word or, followed by your Q. It is cold. It is cold, period. So your P or Q, or the disjunction of P and Q, is simply the sentence, it is raining or it is cold. Now for the truth values, unlike for the conjunction, in the disjunction, P or Q can be true when at least one of the statements is true. Otherwise, it's false. So let's make a truth table for you to visualize it. Okay, we have P, we have Q, and we have P or Q in here. So we have two variables, that means we'll be making 4 rows, just like what we did for the conjunction. Okay, 1, 2, 3, 4. The same pattern: true, true, false, false, true, false, true, false. Again, for the P or Q to be true, at least one of the statements or one of the propositions are true. Let's have true or true. This is true. True or false. This is true. False or true. This is true. False or false. This is false. So you see, there is only one reason, or there can only be one reason that will make your P or Q be false. That is when both of your propositions P and Q are false. Now let's move forward. Let's go to our fourth logical connective, and that is called the conditional. Okay, conditional, which is in this form, and it can be read as if then. Right? So that is how a conditional statement is. Suppose that I have here two statements, P and Q. Then my conditional statement will be like this: P implies Q, or if P, then Q. So P here, this is our hypothesis or antecedent. Q here, this is our conclusion or consequent. Now for the conditional statement, it can only be false when your P is true, but your Q is false. So this will imply that your P implies Q is false. Again, in this case, there can only be one reason for it to be false, and that is when your P is true, your Q is false. Otherwise, it will be true. Now let's start making a truth table. right, for a while. I'm having a trouble drawing a straight line here. So we have P, Q, and P implies Q. Now we still have two propositional variables here, so we'll have 4 rows again. And the pattern continues. The pattern is just the same. T, T, F, F, T, F, T, F. So let's start. Don't forget, this is the only reason that your P implies Q will be false. Okay? T implies T, that is true. T implies F, right? It's the same with this case, so it is false. False implies true, that is true, and false implies false, that's still true. Now you see there can only be one reason for your P implies Q be false, and that is when your antecedent is true but your consequent is false. Now for the conditional statement, given the form P implies Q, we also have the converse, the inverse, and the contrapositive. Okay, so let me write in here, P implies Q. This is our conditional statement. Conditional statement. Now for the converse, we'll just have to switch the places of Q and P. So from P, this will become Q. Copy the conditional sign, and we have here P. Again, this is for the converse. Converse. We just switch the places of P and Q. Now we also have the inverse. What is this inverse? The inverse is simply the negation of your conditional. That becomes from P, it's not P. Copy the conditional sign, and Q, its negation is not Q. So if we have a negation for conditional statement, then we also have a negation for the converse, and that is called the contrapositive. Contrapositive. So from Q, this will become not Q. Copy the implication form or the conditional form, and we have from P, this becomes not P. Okay, so again, the original form is the conditional, that is P implies Q. Now, we shift or we change the places of P and Q, then that becomes a converse. Okay, so inverse is just the negation of your conditional statement, and contrapositive is just the negation of your converse. So let's go and try to have an example. Let's say my P, right? Example. Let's see, or let's say that my statement P will be today is Sunday. And my statement Q will be I will go for a walk. So let's find out the conditional form. Okay, that's P implies Q. So we have here our P, that's the statement today is Sunday. Oh, before we forgot, this is a conditional statement. That means we'll be using if and then. So we'll have if first, followed by our statement P. Today is Sunday. Today is Sunday. Then I will go, right? I will go for a walk. Next, let's go and find the converse. So we have Q implies P. We'll start with if, followed by our Q, that is, I will go for a walk. If I will go for a walk, then today is Sunday. When today is Sunday. Now let's have the inverse form. So for the inverse form, we can say simply that, I'll just dictate this, okay? For the inverse form or the negation of your conditional, let's just say, if today is not Sunday, then I will not go for a walk. Okay? If today is not Sunday, then I will not go for a walk. That will be your inverse. Okay, if today is not Sunday, then I will not go for a walk. Now for the contrapositive, that will be the negation of your converse. So we have not Q implies not P. The sentence will be, if I will not go for a walk, then today is not Sunday. Okay, so we already have the 4 logical connectives. This time, let's have the 5th logical connective, or the so-called biconditional. Biconditional. So the biconditional is given by this symbol, and it's read as if and only if. Okay, if and only if. Now let's go and continue. Suppose P and Q are statements, then my compound statement using the biconditional would be P if and only if Q. That is how we will read that. P if and only if Q. So it is two-way. It is true for P implies Q, and it is also true for Q implies P. Now suppose that my statement P will be x plus 2 is equal to 5, and my statement Q will be the statement x is equal to 3. So my biconditional statement having P if and only if Q will be x plus 2 equals 5 if and only if x is equal to 3. This means that it is true for x plus 2, or if x plus 2 is equal to 5, then x is equal to 3. And it is also true if x is equal to 3, then x plus 2 is equal to 5. Okay? For a biconditional statement, both of your propositions P and Q should have the same truth values for the P if and only if Q to be true. Now let's make a truth table. Okay, truth table in here. Forgive me for my drawing for my table. So we have propositional variable P, propositional variable Q, and we also have the biconditional statement P if and only if Q. Now there are 2 variables involved, so we'll have 4 rows. 1, 2, 3, and 4. The same pattern, true, true, false, false for the first column, followed by true, false, true, false. So again, for this particular statement to be true, both of your P and Q should have the same truth value. T if and only if T, that is true. T if and only if F, that is false. F if and only if T, still false. If and only if F, that is true. So as you can notice, it can only be true. P if and only if Q will only be true if P and Q are both true, or P and Q are both false. In short, they pair or they have the same truth values. Now, before I forgot, I want you to remember these 3 terms. We have the term tautology. We also have contradiction, right? Contradiction, and the other term, contingency. Okay, so when can we say that it is a tautology? That is, if the last part of your column for the truth table are all true. Or if your conclusions are all true, then it is called a tautology. On the other hand, if all the truth values in the last column or all of your conclusions are false, then it is called a contradiction. Right? A contradiction. But if it's neither a tautology and neither a contradiction, then it is called a contingency. Okay, so let's try to construct a truth table. Let's have it here. Construct a truth table for construct a TB. I'll just write TB in here. TT rather. Oh, I'll just complete it. Okay, for a while. Construct a truth table for, okay, we have here not P and Q implies not Q implies P. So we'll write down the first row first. So the first row will be your propositional variables or your statements, starting from the single ones to the compound statement until the last. So let's consider or let's rename the entire statement as A. Okay, so that later we won't be having troubles in writing this because it's too long. So we have the first variable, we have P, we also have Q, and then we have not P. Take note, we have a compound statement here, not P and Q. We also have the other statement here, Q implies P, Q implies P, and the other compound statement here, not Q implies P, and on the last column would be this entire thing, or we used to represent that by using the capital letter A. So let's put a line in here. Let's draw a line in here. We'll divide this by columns. Okay. I'm sorry for my drawing. So still we have two variables in here. Now we'll have 4 rows. We'll make 4 rows. 1, 2, 3, and 4. So the same pattern, true, true, false, false. But take note, you can have 3 or more variables. That depends on your sentence. And here we have true, false, true, false. So let's get not P. We have a P here. We have not P here. That means we're taking the negation of our P. So if my P is true, my not P will be false. If my P is true, my not P will be false. If my P is false, my not P will be true. If my P is false, my not P will be true as well. Now let's have not P and Q. So let's go not P and Q, this particular column in here and this particular column in here. We have and. That means both of them should have the same truth values, or both of them should be true. Okay, both of them should be true. Now let me remove the circle. Not P and not Q, not Q rather, not P and Q. So we have F and T, that is F, F and F, that is F, T and T, that is true, T and F, that is still false. Now let's go for the Q implies P. So we'll start from Q to P. This is implication or conditional statement. That means there is only one way to make it false, and that is when your first proposition or your antecedent is true, but your consequent is false. So in that case, it will be false. Now let's continue. Q implies P. So T implies T, that is T. F implies T, that is T. T implies F, that is F. F implies F, that is T. Now let's have not Q implies P. So the negation of this entire column. Negation of T, that is false. T, that's false. False, that becomes true. True, that becomes false. Now we are down to our final statement. So we have not P and Q implies, right, so we'll be using this one. Not P and Q implies this statement, not Q implies P. So we'll start here. So implication again, this can only be false if your P or the first proposition or the first statement is true, your antecedent is true, but your consequence is false, then you'll have false in here. This will be the only case. So let's begin. F implies F, that is T. F implies F, that is T. T implies T, that is T. F implies F, that is still T. So you see our conclusions are all true, then that means we can consider this one as a tautology. Okay? Now let's have another example. Let's construct the truth table or construct the truth table of not P and P. So in this case, we only have two variables that from 2n that becomes 2 raised to 1. So we have 2. 2 divided by 2, then we'll have 1 true followed by 1 false as our pattern, and we only have 2 rows in here. So let's draw the truth table. Okay, we have P, we have not P, and we have our final statement, not P and P. Now we only have 2 rows in here, 1 T, 1 F. So if my P is T, my not P will be F. If my P is F, my not P will be T. Now let's have the conjunction of not P and P. So it uses and. It uses conjunction. This means both not P and P should be true. Now we have T and F, that is F. We have F and T, that is still F. So all of our conclusions are false, then that means it is a contradiction. Now, if it's neither contradiction nor tautology, then it's considered as a contingency. I hope I made this clear. Now, if you have questions, feel free to ask me. Okay, goodbye and God bless us all.